Okay, I wanted to talk to you a little bit about some stuff for non-uniform circular motion as well as bank curves and this vertical circular motion thing. So far we've talked about horizontal circular motion on a plane. So there's a surface and this object is rotating in a circle, and we know there's like a normal force, a gravity force, an inward pointing radial force, and occasionally we would have like a outward pointing friction force. We also had this scenario where we were spinning it over our head, and so it was going down at some angle theta below the horizontal, and then it was making this circular rotation. And again, we would have a inward pointing radial force, we would have a gravity force pointed down, and we would have this tension component pointed upwards that would cancel out the gravity component. And then our inward radial force would also be basically the x component of tension. So that's how we did those two horizontal rotations, but this one is a little bit different because now the forces are going to constantly be changing. So whenever this thing is in motion, if there is a inward pointing radial force, it is constantly changing. You can see that by this diagram where at the bottom here we have mg and ft being exactly opposed to each other, and they're the same length. And then up here at the top we have mg and ft being added together, so they're not in this, they are now in the same direction at top. They're in opposite directions at the bottom. And so because of that, we have some component of this tension force that will be canceling out gravity, and some component of it that will be on that radially accelerating circular path. So we talked about swinging the mass vertically. We could basically apply the same tricks that we did to the other circular motions. And those tricks are we sum the forces in the x direction, and we get max, and we sum the forces in the y direction, and we get may. But now, instead of thinking about it as max, let's just think about it as the sum of forces in the radial direction, right? So radial direction would be, if I'm sitting here, my radial direction would be this way. At this point, my radial direction will be that way. So this is very similar to just how, if we looked at the side-on view of this block or this mass being rotated, where this is our positive x direction, this is also our positive radial direction. And so what we're doing now is we're saying that just from the beginning, sum of forces in the radial direction is equal to ma sub r. Without making that argument that x is actually the radial direction and all that stuff, we're just starting off here. Sum of forces in the radial direction is ma. So vertical uniform circular motion is slightly different from horizontal uniform motion because gravity is always acting and the tension force must constantly change to keep up with linear velocity and to maintain the radial acceleration. So there are a bunch of problems we could do with that. The first one is, let's say we have a 0.145 kilogram ball on the end of a 1.10 meter long string. The string has negligible mass, so we don't have to worry about that. And it's swung in this vertical circle. And we want to determine the minimum speed that the ball must have at the top of the arc so that the ball continues moving in a circle, and calculate the tension in the chord at the bottom and top of the arc if the ball is going twice as fast. I think we'll just do the bottom. I'm sure you can figure out how to do the top. But first of all, if I draw a picture of this, I will know here is my circular path. Here at the top, my gravity force will be pointing down and my tension force will be pointing down. Here at the bottom, my tension force is pointed up and my gravity force is pointing down. So if I think about this, in the radial direction, this at the top, this is going to continue on the motion as long as this tension force is greater than 0. If the tension force is not greater than 0, mg cannot change its direction. It always points straight down. And so once it leaves that top of the circle position, once the mass moves, say, to here, now if the tension is no longer acting, gravity is pointing directly down, just gravity, and this is no longer radial acceleration. It'll be accelerating in more of an oval shape if we were to have this happen. In fact, it'll end up being like a parabolic shape that we'd expect from projectile motion. Right? Start off with some initial velocity vx, and vy would be 0, and then eventually all that vx becomes eventually all of that distance difference ends up increasing the y velocity. And so down here you have that vy and vx as well. And that's what we would expect if gravity were just to act. However, if there were a second force, a tension force pulling it radially inward, this parabolic path would just kind of continue on being more of a circle and less of a parabola. So to start this off, like I said, we want a situation where our tension is equal to 0. Because if the tension gets bigger than that, then we will have the good situation where this object keeps rotating in a circle. So if I write my forces in the radial direction, I get T and plus or minus really Fg is equal to ma sub r. So this would be for the bottom, it would be a negative sign. If we were at the top, it would be a positive sign. And then if we were somewhere in between, we'd have to decompose our vector. But if t equals 0, then what I get is that force of gravity, Fg, is equal to ma sub r. Right, that's just t being 0. That's our condition that we're saying finds us this critical position. We know mass times g, the constant gravitational acceleration, is our force of gravity. And we know ma sub r, but a sub r is also equal to v squared divided by r. And this introduces that v that we are looking for to determine the minimum speed. So this tension being equal to 0 makes this v v minimum. On both sides of this equation, I have a m, and so if I cancel those, if I divide through by m, I get g is equal to v squared over r. This is basically saying that our acceleration due to gravity at the top is g, and g is a sub r. So that tension is 0. Okay, so if I solve this thing for v, I get v is equal to the square root of g times r, which is the square root of 9.8 meters per second squared. And this is a positive 9.8, not negative, like we had in kinematics. This is positive. So 9.8 meters per second squared times 1.10 meters in the square root. If I plug this into a calculator, the answer I get is 3.28 meters per second. So that's the answer for part A. That's the velocity at the top of the motion. And then if we say that v2 is equal to 2 times v, then our equation that we had before, which was Fg is equal to m a sub r, or mg is equal to m times v squared over r. This is where we just replaced Fg with mass times gravity, and we've replaced a sub r with v squared over r. If I do this substitution, again, this will be our v2, right? Then if I plug in for v2, that v2 is equal to 2v1, and I also cancel my masses, then I get g is equal to 2 times v squared over r. And that is then 4v squared. So I know, actually, let me take a step back on that. This actually, v sub 2 equals v, that's good, but we need to use that tension at the bottom of the motion. Tension minus mg is equal to m a sub r, which is v squared over r. And this is again v2. Then if I solve this for my tension force, E is equal to m times v squared over r plus g. We know all of these quantities. We know mass is 0.145 kilograms. We know v squared is actually going to be 2 times 3.28, so we'll call that 656 meters per second squared. So that is 2v squared divided by r, 1.10 meters, plus g, 0.8 meters per second squared. Plugging this into a calculator, I get a tension force of 7.34. This is at the bottom of the motion. If you were to want to try the top of the motion, all you have to do is here in this equation here. In this equation here, instead of using minus, you would use plus because they are pointed in the same direction. You could also say t, negative t minus mg. That would probably be more correct because both t and the force of gravity are pointing downwards at the top of the motion. So if you wanted to calculate the top of the motion one, you just use t plus mg or minus t minus mg equals mv2 squared over r. Go through this whole process again, and you'll get a number that is bigger than 7.3. At this point, I should probably mention that I am sick. I have been sick for the last several days. And if you see any long pauses in these videos, it's mostly because I had to stop and blow my nose or something, or clear my throat. So I apologize for any big lags in timing and stuff, but it's something I have to do. Otherwise, it starts to sound kind of gross. You're rasping and coughing stuff. Anyways, to get the second one, we have what minimum speed must a roller coaster be traveling at the top of the loop to keep passengers from flying out if the radius of the loop is 7.4 meters. So here we'll have maybe a roller coaster does something like this, and the radius of this loop at the top is 7.4 meters. And what we need to do is figure out what minimum velocity will keep this thing on track. So if I look at the force diagram at the top, if I draw a free body diagram, at the top of this motion, I will have a force of gravity acting downwards. This is also a roller coaster, so it's in contact with the track, or if we think about the people in the roller coaster, they're in contact with the roller coaster, and so there is a normal force pointed downwards. There could be a friction force. We're going to kind of ignore any friction force, I think. The two forces that we have now are a normal force because it points perpendicular to the surface at the top, perpendicular to this motion at the top. Perpendicular would be pointed straight down. Same direction as gravity, because gravity always points. So to figure this out, we're going to use a similar trick that involves summing the forces and replacing a sub r with something with v in it. If I sum my forces in the radial direction, this will be equal to m sub r, which is also m times v squared. Our forces involved are going to be both a normal force and the force of gravity, so they are equal to m times v squared. So the normal force, what's going to happen is if the normal force is 0, then the people will not be, there will be no force to stop them from moving in a straight line. Right? That gravity force will certainly help it, but it won't do all of the job. It needs that normal force to counteract and to provide that radial acceleration. So without that normal force, this whole thing will kind of continue on in a straight path, or maybe an arced path, but not a circular path. So if n equals 0, that's when our critical condition comes in. And then I can write this out. Force of gravity is mg, and then we have m squared over r. Same thing happens where our masses cancel, and then we get just g is equal to v squared over r. So acceleration our radial acceleration is the same as our gravity acceleration if normal force is 0. So if I solve this thing for v, I get v is equal to the square root of g times r. If you stop and pause the video for a moment to prove that to yourself, I would really that, so it's also no. But then plugging the values in, g 9.8 meters per second squared, for r, we had a value of 7.4 meters. Plugging this in, the value of velocity I get is somewhere around 8.5 per second. So if your velocity is just ever so slightly greater than 85 meters per second. A circular. That pretty much concludes our uniform circular motion part, with one small caveat, I suppose, and that is this banked and unbanked curves. These are not really truly going to be uniform circular motion, but it's a good approximation of it, and so we'll consider this to be a uniform circular motion problem. So we've been talking about these circular dynamics. We talked about V equals R omega, A sub R is equal to B squared over R, A sub R is equal to R omega squared, F is 1 over T, all these quantities and stuff, and we start putting them together. But another good example of this circular dynamic situation is when we have a car taking a curve. So when you're in this car and it's making this turn, you feel like you're being pushed outwards, even though we know that's not true. We know that it's actually the car that's being accelerated inwards, and we are trying to stay on a straight path, which happens to go push us towards the outside of that path, or the circular path. And so there is no outward force acting on you. It's instead you're just continuing on that straight line, and the car is being accelerated. You can see this in this diagram that I posted on this packet. If we draw a free body diagram for the car from the front view, we have a normal force and a gravity force acting opposed to each other. The acceleration should be 0. In the x direction, we have this friction force, and it causes our radial acceleration. So obviously we know that there's a radial acceleration, there's some force causing it, and that force here is actually friction. Now, on this one, if I have a flat road, then the only thing that is acting in that direction is a friction force. So on a flat road, the force causing the radial acceleration is just friction. This is like a rolling. And the biggest difference between banked curves, which is when we have, say if we're looking at the front of the car, here's your front of your car. Road, here's the front of the car. A bank curve doesn't have an angle. It's just this thing here. But if we are banking our curve, then it's like this. Now our bank curve says we have an angle, and so that means that there's friction, or there could potentially be friction, but also gravity is playing a part in this whole situation to keep us on. And a lot of bank curves are designed such that you don't actually need friction to continue on that circular path, because gravity will do this work for you, which is kind of an interesting thing to think about, because there's a snowstorm and friction still make it around that curve, as long as you're traveling at safe speed. So if we have on a bank curve or bank road, the forces causing the radial acceleration will be both a friction force and a gravity. So in this section, we will have to deal with a rolling friction, but we will treat it just like a normal friction force. Every part of that tire that is in contact with the road is not slipping. Well, that's the ideal situation, is that it will not slip. Obviously, if we have ice or something that changes it. But for our analysis purposes, it won't slip. And we will model the rolling friction as a static friction, because at any point, the tire portion, the portion of the tire that is in contact with the surface, is resting on that surface and not sliding back and forth. Sliding back and forth is kinetic friction, but that's not what friction does. In fact, rolling friction is closer to static friction, and if you were to slam on your brakes and just skid, that's closer to kinetic friction. So on our these types of problems, we have a banked curve, and sorry, this is still unbanked stuff. In these problems, our curve will be flat, So our car will have a normal force, force of gravity, and maybe some friction force, S, or F sub R. That F sub R will be the force that provides us with our radial acceleration. So if we want to do a problem with this, we can try this one here. This is a 1,000 kilogram car, takes a curve on a flat road, so not banked, and the radius of the curve is 50 meters, and the car's speed is 50 meters per second. Will the car follow the curve, or will it skid? If A, the pavement is dry, coefficient friction is 0.6, or B, the pavement is icy, and the coefficient friction is 0.2. I think you can already tell what's going to happen. If the friction is high enough, pavement is dry, we will expect it to go around the curve, no problem. If it's icy or wet, maybe not so much. So the first thing that I want to do is I need to know how much friction, what is the maximum amount of friction I can get? Or was it, sorry, not the maximum friction I can get. What is the amount of friction that the car will experience when it goes around this turn? So to do that, we need to look at our x and y directions. The sum of the force in the y direction equals 0. That's just E sub r is 0. And that tells us that our normal force is equal to the force of gravity, which can be calculated using the equation mass times constant. So N equal to mg. And we need this because we are going to do our x sum friction term. So in the x direction, the only force that we should have is friction. Or so this will be equal to m a sub r, which is also equal to m times squared over. Now, I need to calculate my normal force because to calculate the normal force, or to calculate the friction force, I will forces. So if I plug in m is 1,000 kilograms, g is 9.8, positive 9.8 meters per second squared, I get an answer of 9,800 newtons. My normal force. Focus answer. Okay, so I also need to know what kind of force I should expect, just from the car, that the car will experience regardless of whether it's icy or not. There's going to be some amount of friction that's going to be required to keep this car on the circular path. That's what we're trying to calculate. So we know mv squared over r, this net force thing, or this friction force, is going to be equal to mv squared over r. We know mass is 1,000 kilograms. We also know that our velocity is 14 meters per second. We square that, so that's for r, it's going to be 8 meters. This should not be meters per second. This should be kilometers per second. Kilometers per hour. 50 kilometers per hour is equal to about 14 meters per second. That's why this is 14. Okay, so I can calculate that, and that tells me that my total friction force, F sub r, is equal to about 3,000 newtons. So I will need to figure out the maximum amount of friction that each of these scenarios, u sub s equals 0.6 and u sub s equals 0.5. I will need to know an equation that I can just basically plug in my mu sub s value and calculate, compare it to this 3,900. If it's greater than 3,900 number, then the surface and car interaction will be great enough to actually will be greater than 3,900, and so it can handle that much friction. But with a lower mu sub s value of 0.25, the maximum friction will not be as much. To show that, we have equation, F sub S maximum is equal to mu k times n force. We know mu k is 0.6 for the dry condition. Our normal force is 9,800. We calculated that earlier. And so the answer I get to this is somewhere around 5,000 newtons, which is greater than 3,900 newtons. And so Fs max is greater than Fs required. And so it won't slip. Because the surface, all the conditions, can provide even more friction than what the car needs to stay on this path. In the icy case, we have Fs max is equal to us, or sorry that I used Fr and Fs interchangeably. They kind of are in a lot of senses, but they use radiant or rolling. So F rolling is equal to mu rolling times normal force. That is 0.25 times 9,800. And my maximum friction force on the icy surface is, if I plug that in my calculator, about 2,500 newtons. And so that is, about 1,000, 1,400 less than the 39,000 that we need to are moving on the path. And so this will slip because F maximum friction is less than the required rolling friction. Keep this on. So, okay, and so we've gotten to the point where we can start talking about banked cars or banked curves. Now, when you're on, say, an interstate, you might notice that the road is at an angle from horizontal. And this is because we want to help the car go around a curve and give it that radial acceleration due to gravity. If you look at this diagram here, we have a normal force that's pointed in the x direction that will provide our radial acceleration. And then we have a component that is in the y direction that will counteract our force of gravity. We could also have a friction force, Fk, here as well. And then this would be Fkx, and this would be a cosine theta. This would be Fk, not Fk, no, this would Fr, yes. It would be Fr times cosine theta. Fr cosine theta equal to Frx. And we also have a y component of Fry. And so Fry plus the normal force in the y direction equal to our gravity force, and also Frx plus Fn equal to our normal force. Rolling friction, the x component of the rolling friction plus the x component of the normal force will give us our ma sub r. As you can see from that diagram, there's that component of the normal force that points in the radial direction. It helps us on that circular path. And a lot of times it provides a so see how this works out. We should probably start off by using our second law. Sum of the forces in the x direction equals ma sub r. And that turns out to be just our normal force in the x direction. Plus maybe a virtual force is equal to m sub r. From there, we would plug in that the normal force that we concern ourselves with would be f cosine theta. No, sorry, fg sine theta. And the component of the rolling force that we're going to be concerned with will be the rolling force times cosine theta. R. From there, we could do our regular substitutions. Sine theta plus a y Notice how this is ny, the normal force, because our normal force, remember, on inclined plane points perpendicular to the surface, and so we need that that will counteract gravity. So our friction force is uk times ny, that is equal to m. Next page, we could do a little bit more plugging in of stuff. We get mg sine theta plus uk mg cosine theta is equal to m where r, our m's will cancel out, and we will get d sine theta plus uk g cos theta is equal to v squared over r. And this looks very familiar. We should have seen something like this before. In fact, we did when we did the lawnmower question last unit. Same thing with the snow shovel, where someone is pushing down with some force. Might be a friction force. There's also a normal force and a gravity force, and they're pushing on a lawnmower or a snow shovel, and it's moving. And when we did our Newton's sums, we ended up getting these equations, or this as one of our equations of motion. So to try this out, we look at this problem. If we have a car traveling with speed v on a banked curve with radius r, we want to find the angle that a road should be banked so that no friction is required to make this turn. If I were to look at my force diagram, I would notice that in the x direction, I have sum of forces with radial. Yeah, sum of forces is equal to mass times radial acceleration. And the forces that are acting are the x component of the normal force plus the x component of our rolling force, Rx. That equals m. So then we don't want to have any friction. That's the point of the bank curve. We don't want to need friction. So our friction turns 0, and our result then nx and sub x is equal to m times a sub r. But nx is just n times sine theta. That will be equal to m sub r. That's about as far as we go with this direction. So if we go back up to the top and we think about the sum of forces in y direction, that of course will give us a 0 acceleration because it's the y direction. But then if I do my sum of forces, I will have a y component to my normal force, I will have a force of gravity, and I'll have a friction component. Again, that friction component is 0, so you can cross that. This tells us that n sub y is equal to f p, should be minus, because it's pointed downwards. Speed. So the final result is that ny is equal to our force of gravity, which is m times g. And y is n times sine theta. That is equal to mg. If I solve this equation here for n, I get n is equal to mg over theta. You know what? I screwed up. This isn't n sine theta. This is n cos theta. The y component has cosine on it. Okay, so now we fix that. I can take this n and I can plug it into this equation. And what I get is n, which we said is mg over cosine theta. N times sine theta equal to m a sub r, which will unplug v squared over r in for a sub r. I have mass on both sides, so my mass cancels if I divide through my mass. And then what I have is sine divided by cosine in g. So g times sine over cosine is the same thing as g times tangent theta. That's equal to v squared over r. So here, all I have to do is solve this for theta, and to do that, I take the arc tangent, or divide through by gravity, and I get tangent theta is equal to v squared over g times r. And then taking the arc tangent gives me theta is equal to the arc tangent, or the inverse tangent of v squared over. Here we have our expression that gives us our angle if we want to be the zero friction condition for a bank curve. So that's interesting. And if we were trying to take a curve at a higher speed, could we add additional sandbags to the vehicle to help maintain condition for the bank curve? If so, why? If not, why not? This one takes a little bit of thinking, but if we just look back to the previous problem we did, we see that our angle theta for a zero friction condition is equal to a arc tangent of v squared over times r. So really, when we do these bank curve problems, the important things are the maximum velocity you can travel to keep that no friction condition, the radius of the curve, and the angle that banking is done at. Anything else isn't really important. And as it turns out, when you look at this equation here, there is no mass term. And so because there's no mass term, and that's because there's no friction involved, they're adding additional weight to your vehicle. Sandbags isn't going to help. The only time that it will help you is if you are expecting to encounter friction, because our friction force goes something like mu sub r times our normal force in the y direction, which is about equal to sub r times mg cos. So here, if we have friction, then the mass term does appear, but the thing is that it's going to be appearing as a part of a sum, right? And that sum is going to say something like mass times v squared over r plus u sub r m g cos theta plus our normal force being, the normal force. These also have an m in them. So even if we did have friction, the additional mass won't help you. So the answer is no, it won't help. And the reason why is because there is no mass. There is no mass term. Box. But you get the idea. So yeah, because even if we did encounter friction, still that additional mass through the what do you call it? Through the sandbags isn't going to give you any additional traction. It's not going to help you in any way, shape, or form when it comes to the bank curves. So let's see, what do we have next? One more problem for bank curves. A 1,200 kilogram car is rounding a curve, and the radius of that curve is 67 meters, banked at an angle of 12 degrees. If the car is traveling at 95 kilometers per hour, will a friction force be required to keep the car in the circular path? If it is, how much? So how many newtons of force will the friction force have to be for us to continue on the circular path? The first thing that we need to do is we need to know what is the tangential or linear velocity of this circular path. And we can find that by going through the same arguments that we did before. We'd say the sum of the forces in the x direction is equal to ma sub r. And those forces, if you recall from that diagram from a couple pages back, those forces will be a friction component, f sub r x, and it will be in the negative direction. Oh, sorry. Yeah, it will be. Then we will also have a a normal force component that will be pointed radially inward, so it's positive. And we will also have, well, no, that's it. So this will be equal to ma sub r. And we want the condition, however, that there is no friction, and so this friction term goes away, and so we're left with nx is equal to ma sub r. But nx is equal to n times sine of theta, that equals m a sub r. But a sub r is v squared over r, and n is going to be mg. So we get mg sine theta is equal to m times v squared over r. In the y direction, sum of forces in the y direction is equal to 0, because our acceleration will be 0. Our y forces will be ny minus a friction force in the y direction minus the force of gravity. Again, friction will be 0, so we can ignore that, and we get ny is equal to fg is equal to mg. But ny is equal to n, the normal force, times cos theta. If I solve this part of the equation for n, I get n is equal to mg over cos theta. You should see a similar type of thing happening as what happened in the first problem for bank curves, where we end up with this n is equal to mg over cosine theta, and then we're just going to plug that in for this normal force over here. So then I get mg over cosine theta, which is our n, so n times sine theta, is equal to m times a sub r, or v squared over r. Our mass terms cancel on both sides, and then I get g times sine over cosine, so that is g times tangent theta is equal to v squared over r. V is equal to the square root of, oh, sorry, we were solving for v. Yeah, so v is equal to the square root of g times r times tangent theta. Plugging in values, I get the square root of 9.8, positive 9.8 meters per second squared, times my radius. What's the radius of this one? 67 meters, times tangent theta, which is tangent of 12 degrees. So again, this is all in the square root. And the answer I get for that is my velocity v is equal to 11.81 meters per second. Now, this is the case for zero friction, but there always can be friction. So if we want to know, will this work out, what we have to do is try to basically just force a friction term in there, and then see if it ends up being 0. If it's not, it'll end up being a number, and we'll know what that friction value is. So separate this half of the paper, and to do this, I get I start off summing my forces in the x direction, get ma sub r. Forces in the x direction will be nx plus, in the x direction, our friction force will be pointing, here's our inclined plane, and our acceleration is this way, so our friction force is this way, which means that we will have a nx minus friction, minus frx, is equal to ma sub r. Okay, so I had to stop and review some of this. Turns out that this is actually going to be positive. Our friction force is going to be down the incline as well, because our tendency would be to move outwards So our direction of motion, our delta x that our body would want to take if it were not attached to a vehicle, would be outwards, and so our acceleration would be actually inwards due to friction F sub r. So it is positive as well. So we have n sub x plus F sub r, x is equal to ma sub r. I can replace some stuff, so I get nx plus F sub r. Well, that's mu k times n. I think it's going to be better to just leave it as F sub r for the time being. F sub rx. However, our nx term is going to be n, the normal force, times sine of theta, plus our friction force, F sub rx, equals m times b squared over r. In the y direction, this is equal to, we will have a normal force, a positive normal force, a negative force of gravity, and a negative rolling friction in the y direction. And this will give us, will be equal to 0 because our acceleration should be 0. And the a sub y is equal to 0. Ny is n times cos theta minus fg, which is just mass times gravity, minus f sub ry is equal to 0. So what I'm going to do without any prompting or any real reason is I'm going to go ahead and take this equation, I'm going to call it equation 1, and this equation, I'm going to call it equation 2. We know that Frx, the friction force in the x direction, that is going to be our rolling friction times cosine theta, right? And we can look at this thing. Here's our friction force this way. Here's the x component over it. Here's theta. And so this x component of friction that is right here, Frx, is equal to the hypotenuse, Fr, times cosine theta, because it is adjacent to this angle. Because Frx is adjacent to the angle. So we get n sine theta plus Fr cosine theta is equal to ma sub r. This is our new equation 1. And equation 2, using a similar thing, is n cos theta minus mg. Actually, let's go ahead and forget that. So it's n cosine theta minus Fry, which is Fr times sine theta. And if we move our mg to the other side by adding mg both sides of equation 2, this is what we get. So without any real prompting or reason or, other than my own personal experience, I'm going to multiply one of these equations by cosine and one of these equations by sine. And the one that I'm going to multiply by cosine is equation 1. And the reason why I'm doing that is because I will get a cosine squared term multiplied by f sub r. And if I multiply the equation 2 by sine, I get f sub r sine theta. And you'll see what happens when we do this. So if I multiply equation 1 by cosine, I get n times sine theta times cos theta plus f sub r times cos theta squared is equal to ma sub r times cosine theta. Same thing, or a similar thing with equation 2. I get n sine theta cosine theta plus f sub r sine squared theta is equal to mg sine theta. So why would I do this? Well, there's some things you can maybe notice. Also, maybe you notice I made a mistake. This should be negative. You might notice that this term, this n sine theta, cosine theta term, is present in both of these equations. So if I subtract them, that term goes away. Also, you'll notice that this term is negative. So if I were to subtract FR cosine squared theta from, subtract FR sine theta from FR cosine theta, but FR sine theta is already negative, then I'm basically getting this term that will have sine squared theta plus cosine squared theta, and that'll simplify a little bit. So let's go ahead and subtract these things. On the left-hand side, I have n sine theta cosine theta minus n sine theta cosine theta. That goes away. Plus f sub r cos squared theta minus a negative f sub r sine squared. We're running out of room here, so I'm going to go ahead and just copy this piece here. And I'm going to insert a blank page so we can finish this on. About that. Okay, so if I paste this back in, I have n sine theta and cosine theta. That's horribly written because it's running out of space. So let me fix this. My first equation was n sine theta cosine theta plus f sub r cosine squared theta. And then my second equation, which I'm subtracting, was n sine theta cos theta minus f sub r sine squared theta. And this will be equal to m a sub r minus mg. I forgot that this has a cosine on it, minus mg sine theta. Okay, so now we have a positive n sine theta cosine theta minus n sine theta cosine theta, so those go away. I have a common f sub r, and now notice how this is a negative, and this is minus a negative, and so this becomes f sub r cos squared theta plus f sub r sine squared theta, still equal to m a sub r cos theta minus mg sine theta. I can factor out this f sub r from both terms, and I get a cos squared theta plus sine squared theta. If you recall from your trig class, which I'm sure many of you have not taken yet, but there's a relationship that says when you add a cosine squared to a sine squared, this is equal to 1. Why this happens, it involves, your unit circle and all that stuff that you'll learn about next semester, but it's just a identity that you should know, that you should memorize, and that is cosine squared plus sine squared equals 1. There's about 3 of them. Cos squared plus sine squared is equal to 1. I think it's something like secant squared minus 1 is equal to tan squared. And then there's another one. I don't remember the third one at all. But these are all derived from Pythagorean identities, right? This is basically saying a squared plus b squared is equal to c squared, where c is equal to 1. So all of these are just different ways of arranging a squared plus b squared equals c squared. The result that we get as far as our unit circle result is that cosine squared plus sine squared is equal to 1. So this f sub r times cosine squared theta plus f sub r times sine squared theta, that whole thing is actually equal to just f sub r. And f sub r is equal to the stuff on the right-hand side, which is m times a sub r cosine theta minus m times g times sine theta. I can factor out a common mass, and I'm just going to go ahead and start plugging stuff in. So my 1,000 kilogram mass times, factored out because there's a mass in both terms, times a sub r, which is also v squared over r. A sub r which is 26.39 meters per second, over r, 67 meters. This is our a sub r term, equal to v squared over r, times cosine of 12 degrees, minus mass, which is already out front, we factor that out, times g, which is a positive 9.8 meters per second squared. The negative sign comes from this negative sign up here, not from 9.8 meters per second squared pointed downwards in the negative y direction. So minus g sine theta, which is sine of 12 degrees. If I plug this all into a calculator, I will get a force that is 9.8 times 10 to the third newtons, or about 9,800 newtons. This is a very long process. I wouldn't expect you to know this by the time the final comes around. So this unit final is not going to include a problem like this. It will probably include a problem of the form, will it make it? So you're given some information and you have to find out if that information, that scenario is enough that you can make it around some curve without friction or something like that. So I think that's about it. That is pretty much the end of our uniform circular motion. However, there is one more topic to kind of briefly cover. That is our non-uniform circular motion. So uniform circular motion, if you remember, it happens when an object has the same linear velocity magnitude, but different directions. That is, the magnitude of v is constant. And we said some stuff about that, also causing r to be constant and omega to be constant. And also that is related to a sub r also being constant. These are some conditions that you can look for to check and see if uniform circular motion is being followed, because v has to be constant, a sub r has to be constant, and r times omega has to be constant. So the total acceleration, if we don't have this scenario, if we are not undergoing uniform circular motion where the magnitude of v can change, then we can draw a picture maybe. And if we look at our tangential velocity v, it's this big here, and then maybe it's this big here, and then over here it's even smaller, we can see that there's this tangential component of this velocity that is getting smaller. And so to do that, we have to have an acceleration, right? A change in velocity is required by an acceleration. So we have this tangential acceleration that is equal to delta v over delta t. It is also equal to a sub t is equal to r times alpha, where alpha is the radial acceleration, the radians per second squared acceleration. So the total of acceleration, the total acceleration vector for non-uniform circular motion now has two components, whereas in uniform circular motion it only had one, and that's the inward pointing radial acceleration. But now we have this change in the tangential velocity's magnitude, and so that requires a tangential acceleration. And so our inward pointing, let me get a different color here, inward pointing radial acceleration, there's also this tangentially pointing tangential acceleration, a sub t. And so our total a vector is equal to a sub t vector plus a sub r vector, our radial vector, plus our tangential acceleration. If you remember, there's a Pythagorean theorem that we can use, which says that the square root of at squared plus ar squared is equal to our total acceleration. So if we want to find the magnitude of the total acceleration, we would need to know the tangential and the radial accelerations, square them, add them, and take the square root, using the Pythagorean theorem. There's our scratch work. stuff. All right, so if you do recall this from one of our earlier discussions, and also from just a few minutes ago, I kind of jumped the gun on this, but there is a relationship between our a sub t, our tangential acceleration, and the angular acceleration alpha, and that is a sub t is equal to r times alpha. So non-uniform circular motion again involves rotations where the object speeds up or slows down its rotation. This means that we can have a omega final and an omega initial, a theta final and a theta initial, and a constant alpha. As it turns out, the r doesn't change, or maybe it can, but in non-uniform circular motion, we kind of expect our tangential acceleration to be uniform. That is constant, and as a result, alpha also remains constant. So we have a constant acceleration, and we have a theta final, theta initial, omega final, omega initial, constant acceleration, and maybe some time. And this might kind of ring a bell for you because kinematic equations had those same quantities, but they were linear velocity final, linear velocity initial, linear acceleration that is constant, and a linear position x initial and x final. So as we discussed in kinematics, we said that there must be a constant acceleration. Before we said it was a linear acceleration, even though we didn't know it was linear acceleration. But now, if we know that our angular acceleration is also doing that same thing, is also constant, then it will fit the same criteria that you need for kinematics and linear dimensions. So constant acceleration for kinematic equations to work. The same is true of angular kinematics, but the angular kinematics must have a constant angular acceleration. We call alpha, the Greek letter alpha. So if an object is undergoing this constant angular acceleration, then a object will travel some distance theta in a circle at some angular velocity omega and a constant acceleration of alpha. As always, time is present in our description of motion too. There's always going to be a time component to motion. It's always there. So we had, I kind of briefly touched on this earlier in this unit, where we have these analogies between a velocity and an angular velocity, or a linear and angular velocity, omega and v, and theta versus x and all those things. But we have kind of here describing that relationship, or those analogies, where before we saw the equation v final is equal to v initial plus at. Now we have omega final is equal to omega initial plus alpha t. Right? Same equation. It gives you the same information, but one of them has angular quantities, one of them has linear quantities. So what this allows us to do is basically, if we're going to change our radius, and maybe our omega will change, we can figure out what that final omega is. If we know how long it will take to do something, we can calculate how much angle it swept out, or how much change in velocity there was. So this is a really useful tool to know for your rotational motion. Anyways, we move on to the next page. We have some more statements. Basically, the first equation tells us that an angular acceleration will result in a change in angular velocity over time. And to put that mathematically, alpha is delta omega, change in velocity, over delta t, change in time. Again, we can always say that t initial is 0, and so t final minus t initial is just t. So we can write delta omega over t is alpha. The second equation, that is our theta is equal to omega naught times t. Second equation, theta equal to omega naught t plus 1/2 alpha t squared. This tells us that an angular acceleration spelling. This angular acceleration and perhaps some initial angular velocity, that is 1/2 at squared, omega dot t is our initial angular velocity. Those two things will result in a change in angular position, which we call theta. Third equation is a result that you get from plugging in the first equation. The second equation doesn't really tell us anything new, but it does give us the ability to calculate or find a final velocity given position, acceleration, and time. So some applications. If we the classic one that you will encounter is usually either a record player, which I don't know, most people are not familiar with record players these days. They are kind of a niche thing unless you're a DJ or something. But the other one is this centrifuge. So if we have this barrel, and we all, I'm sure, know what a centrifuge is, and explain that. But if we have a centrifuge, it will rotate from 0 rotations per minute to 20,000 rotations per minute in 30 seconds. And the question is, what is our average angular acceleration during that time period? Also, how many revolutions will a centrifuge turn during that period? So the first question might be easy to kind of think of. Maybe we could even come up with an answer without using kinematics. It wouldn't really be that hard. We could just, use the average angular acceleration equation. Alpha is equal to delta omega over t. That would certainly give us the answer. We could also find that from equation 3, I think. But in the end, that second part is what is hard. How many revolutions did the centrifuge turn during that 30-second period? Because it'll turn some number of revolutions, but it's omega, the number of revolutions per second that it will complete is increasing. And so your first second, you will do some number n rotations. Your second will do a different number m, where m will be greater than n. And then the third second, it'll just keep repeating in that fashion, where it'll do a third number of rotations p, where p is greater than m, which is greater than n. And so you have to add all this stuff up, and it's not easy to really think about. But if we use angular kinematics, it becomes a fairly straightforward process. So here's a problem, an application problem. We have a centrifuge rotor is accelerated from rest to 20,000 RPM. That gives us that omega initial is 0 meters per second. And omega final is this 20,000. Well, actually, that's not omega. That is a frequency. A frequency is 20,000 RPM. So we'll need to convert this frequency to an omega, but it is a final. It will give us our omega final somehow. We know time is 30 seconds. And that's about all we know. So the first thing I would do is I'd try to get this frequency, this linear frequency final into omega final, and we'll use omega final is equal to 2 pi times f to do that. So that is equal to 2 pi times 20,000 rotations per minute. Actually, this will be revolutions. No, sorry, radians per minute. And it's radians per minute because this 2 pi converts rotations to radians, but this was rotations per minute, and now we've only converted rotations to radians, and so our minutes have been left there. So to get rid of minutes and replace them with seconds, we will divide by 60. When I do that calculation or plug into a calculator, I get somewhere around 2,094 radians per second. And if you recall, this would be very similar to having a initial velocity, a final velocity, and a time. And what we are being asked for is find alpha. So our equation needs to have alpha, and it will need to have a final velocity and time. And so that equation would be V final is equal to V initial plus A T. So in a similar sense, they are giving us omega initial, omega final, and time, and asking us to find the acceleration. So if you recall from that little thing I showed you a couple of pages back, the analogous equation for rotational motion would be omega final, so angular velocity final, minus omega initial, angular velocity initial, plus alpha, which is angular acceleration, times time. Time does not change in between being in rotational motion versus linear motion. It's always just time. It's a scalar quantity. So how we move through time doesn't matter. It stays the same. So now I have an equation. I have everything I need to know. The only thing I need to do now is solve for alpha. And that gives me, if I subtract an omega initial from both sides, I get omega final minus omega initial is equal to alpha times t. And then divide through by t. Those cancel, and I get that my alpha value is omega final minus omega initial divided by t. Now, this is also the definition of the average angular acceleration. So as I said earlier, you could just use the average angular acceleration for this. You don't really need kinematics. But to answer the second part of the question, you absolutely have to use kinematics. Anyway, so omega final is 2094 radians per second minus 0 divided by time, which is 30 seconds. And what I get is 2094 divided by 30 in units of radians per second squared. When I plug this into a calculator, I get 69.8 radians per second squared, and that is my alpha value. I'm running out of room here, so I'm going to go ahead and insert another page. I will need this. So, new page, we have our value of alpha. We also have that omega initial is equal to 0. Omega final is 2094 radians per second, and time is 30 seconds. So now if I want to know how many radians I will have swept out during my circular motion, I will take delta theta is equal to 1/2 alpha t squared plus omega initial times t, and just basically plug in numbers at this point because we're trying to solve for delta theta, that is our distance. So delta theta is equal to 1/2 times alpha, which we found to be 69.8 radians per second squared. Our time was 30 seconds, square that, plus our initial velocity, which is 0 times time. And the answer I get to that is 31410 radians. The question specifically asked for how many revolutions, and so this is radians, and we'll need to convert that to revolutions using 1 revolution over 2 pi radians. So when I do that, I get about 4,999.0-ish revolutions. So just 1 revolution short of 5,000 total revolutions that would have happened during that 30-second period of time where it's speeding up. So we have 2 types of things that we can describe now. We can describe when something is going in a circle as if it's always been going in the circle. So when we start our analysis on this, we wait for it to reach that uniform circular motion part, and then we can use our uniform circular motion stuff on it. We can also now look at before it reaches that point. We can also say starting from rest, and if I start swinging this thing around in a circle, it'll evolve the equations, the kinematic equations will tell you at some time it'll be this omega, at some time it'll be this alpha. Well, alpha's constant, but at some time it'll be this omega, at some time it'll be this angle, this delta theta. So I do have another problem here. An object starts from rest, accelerates uniformly, and I've got that all worked out. I don't want to go through that. I think I'll leave that one up to you if you're really interested in it. Go ahead and do that. It's always good to get that extra practice in. But I've already gone on significantly longer, about 30 minutes longer than I intended to on this video. So I apologize for how long this was. Let me know if there are any unclear parts or where, if anything needs to be edited, and I will try my best to take care of that. But unfortunately, I'm still not feeling very well. I'm still pausing every few minutes to blow my nose and keep my voice from going too hoarse. So it's been harder. But again, I apologize for not being there, and hopefully we'll see you tomorrow.